So I got a request on the last video, how do you write one of these proofs if you don't have a picture, like if you don't have a graph? And I thought I would kind of go in depth and go all in with this problem here. So we have a parabola, x squared, and just for simplicity, we're only going to look at like the positive half of it. But this is actually a continuous function, no surprise, but it's not uniformly continuous. And I'm going to explain what that is as we go through the example. And so, first of all, why is this function continuous? We've been talking about delta epsilon in this series. And so we want to show that it's continuous at every input. And so let's take an input A, and we're going to show that this function is continuous at that point. And so how do we do that? Well, we take an epsilon, and then my job in this proof is to give you some delta. We're going to fill that in at the very end, and we're going to guarantee that if the distance between our input x and the number a is less than delta, then this quantity down here, we're going to prove that that's going to be less than epsilon. So how is that going to work? Well, without a picture, without any sort of insight, we have to do some calculations. So what is f of x minus f of a? Well, f of x is x squared, f of a is a squared. I can simplify this by factoring. And right away when I factor, I notice that this quantity here has already been featured in our story. I know that that is strictly less than delta. So I'm going to incorporate that into my work. So this is less than delta times whatever x plus a is. Now x and a are positive numbers. That's why I wanted to do the simple case here where we're going from 0 to infinity. So for just ease of not getting into technicalities, this is the quantity x plus a. Okay, so here's where some magic happens. I'm going to ensure, and we'll just make a note to ourselves now, but I'm going to make sure that delta is less than or equal to 1, right? We'll be more precise later. But if that's true, then whenever x minus a is less than delta, that must mean that that difference, if we take the absolute value and get something less than 1, then that number has to be between 1 and negative 1. And now if I do some solving, that means that x has to be within a plus 1 and a minus 1. And then finally, that must mean that x plus a has to be between 2a plus 1 and 2a minus 1. I just added a to all sides of that. It's a little bit small. There you go. And so what that means is as long as we have that delta is less than or equal to 1, I guess these should all be weak inequalities, that this is going to be less than or equal to delta times 2a plus 1, where this is the number that we got up there. So this is a delicate proof. I'm not saying it's easy, but we're just kind of playing around with the inequalities to see what we get. And so now we're really done, because now what I can do is I can say, well, wait a minute. If I were able to say that delta were less than or equal to, say, epsilon over that 2a plus 1, in other words, if I were to say that it was also less than or equal to epsilon over 2a plus 1 up here, well, that would mean that I was done. Because now I could just multiply by 2a plus 1, and I would be done, because these two things are going to equal epsilon. And so I hope what I've convinced you of is that if we know that delta is less than 1, less than or equal to 1, that's going to give us that x plus a is less than or equal to 2a plus 1. We use that right here. And then if we also assume that delta is less than epsilon over 2a plus 1, well, here's delta less than or equal to 2a plus 1. And if we put all of those ingredients together, the purple ingredients, the red ingredients, we show that f of x minus f of a is going to be strictly less than epsilon, right? And so how do we finish this proof? How do we put it all together? Well, let's get rid of all this color coding. So how do I know that there's some number delta that's less than or equal to both of those? Well, I can just take delta equals the min of those two numbers. So I have two positive numbers. Their minimum is going to be less than or equal to both of them. And that's going to do everything that I needed to do in this proof. So one thing you may be wondering, wait, why is that delta allowed to depend on epsilon and a? Well, in our proof, when we're talking about continuity, delta was defined after we had already introduced a number a. And so that number a is allowed to be part of our definition of delta. Just like similarly, we had already defined epsilon earlier. And when we declared delta, that's why we're allowed to have delta depend on epsilon as well. Now, this word uniform continuity or uniformly continuous, sometimes with continuous functions, it's possible to define a delta that works without reference to that number a. And if that happens, then we say the function is uniformly continuous. Now, we cannot do that in this case, and I want to try to explain why. So in other words, the fact that I had to use an a in this formula, completely correct for a continuity proof, but not enough for a uniform continuity proof. And I want to show that this dependence on a is actually required. Okay, so how are we going to show that our function is not uniformly continuous? Well, I'm going to let epsilon be, I don't know, let's take the number 7. I can really make it anything in this. And I'm going to show you that no matter what you let your delta be, if you let it be any number, I am going to find two numbers. I'm going to find two numbers, x and a. And I promise you that the distance between those inputs is less than delta. I'll explain where they come from in a second. But I'm going to show that the distance between their outputs, I'm going to convince you that that is greater than 7. In other words, it's greater than epsilon. And so this cannot be a delta that works in the proof. And so let's see how that works. So I am going to define a to be some mystery number. We'll fill that in at the end. But I want to ensure that x minus a, I want to make sure that that distance between those inputs is less than delta. So how can I do that? Well, I get to pick both x and a. So why not just ensure that they're like delta over 2 apart? Right? So let's make x be whatever a is. We'll just add delta over 2 to it. Right? So now we've got two positive numbers. I guess a hasn't been defined yet, but their difference is definitely less than delta. So now we work it out. We see f of x minus f of a. We look at what we get. So what is it? We do some simplifying. As before, we get x minus a, which is delta over 2, so we have that. And now x plus a, well, whatever a is, when we add x to it, we're just going to be adding delta over 2 plus a. And so this is like our x, this is our a. And when you simplify all this down, you see that we get actually delta squared over 4. And then this 2a that cancels with the 2 in the denominator, and we just get a times delta. And if I'm trying to show that this is bigger than, say, 7 or epsilon or whatever number I have, I think it's pretty clear how to do this. Because I get to define a however I want, and so I'm going to say a to be 7 over delta. So when I do that, I calculate. This is going to be delta squared over 4 plus, well, 7 over delta times delta. And what is this? This is 7 plus delta squared over 4. And I promise you that no matter what delta is, this is going to be strictly greater than the number 7. And so I've shown you that no matter what delta you pick, even if it's really small, I can find two numbers, a, this number, and x, this number, that are within a distance of delta of each other, but the difference between their outputs is not within a distance of 7 of each other. And so if I can't even keep the outputs within a distance of 7 from each other, there's no way I can do it for an arbitrary epsilon. Okay, maybe this was too much to try and do in one video, but thank you for watching. Have a great day.